Okay, well today I would like to introduce the conditions for regularity, but in the same way in which they were discovered. It's not necessarily the way that one would present them writing it up some years after, but I want to sort of motivate the way they are found, because they were found by a fairly classical approach to the problem. So first let me recap a bit from last time. So just recall that we're studying this Monge-Kantorovich problem, and we're given a cost function C, and so far we've only needed to put two derivatives on C. And let me not mess around with subsets. Anyone can go through later and take smaller sets than Rn cross Rn, particularly when you see examples. So let's just suppose C is defined everywhere, and I won't have to fuss with conditions relative to an initial domain here. And let me introduce two conditions which we saw last time. First one we call A1. This is that these derivatives, the x derivatives as functions of the second variable, and the y derivatives as functions of the first variable are 1 to 1 for all values of the x here and the y there. And we also assume that the relation between these and their inverses is smooth, and the determinant of c sub xy is not equal to 0, so that's the mixed derivative with the x and the y variables. And remember that this problem was given two, I'll just simplify things a little now, given omega star in Rn and mass balance. So we're given two functions f and g, non-negative in L1 omega, L1 omega star respectively, but let me just take them to be positive now. I won't worry about possible vanishing of these functions, and they satisfy this mass balance condition, integral of f equals integral of g. And the Monge-Kantorovich problem in the form that I was presenting, it was the maximizing problem. Find the max over this class of measure preserving mappings, or mappings that push forward the measure of density f to the measure of density g. This cost functional c of t, which is the integral of c integrated against the density f over omega. And we saw that this is solvable under these conditions. This will be solvable this is solvable with a solution given by t equal to the inverse of this c sub x dot of a gradient of a function u, ae, for and this potential had a property that it was C convex, potential u, and of course that implied other things, that this implied that it was semi-convex, twice differentiable almost everywhere, etc. And I didn't prove this last time, but it's not a bad exercise, that this potential u satisfies a Monge-Ampere type equation almost everywhere. That first of all we have the C convexity implies this ellipticity condition, d2u greater than dx squared, greater than or equal to dx squared c dot y dot du AE, where y is defined to be this inverse and determinant of d2u minus, again, dx squared, the determinant of this quantity c dot y dot du is equal to determinant of this mixed derivative cxy, absolute value f divided by g composed with y. Remember, in here we've got a dot and a y and AE. And this we call the optimal transportation equation. You can show this simply by approximating by modifiers and then using the fact that they converge almost everywhere to the Hessians of the modifiers converge AE to the Hessian of the function, and then show that the measure preserving condition is preserved in the limit. And we also know that T is unique, AE, and it's also 1 to 1 AE. Of course, an equation like this almost everywhere is absolutely meaningless. Any sawtooth function of one variable satisfies u double prime equals 0 AE. So it's not a great statement, and what we want to do is show that under appropriate conditions these potentials will satisfy this Monge-Ampere type equation in a classical sense. Okay, so let me now start talking about interior regularity. Our object is to find conditions which will imply that such a potential is locally smooth the interior of the domain. We could also approach the problem of global regularity. It's a completely different sort of approach.
So in a specific case of C is the distance function, one can write down this T.
Yes, and our mapping T, the mapping T that solves this problem is given by the y dot du. Yes, and so to solve this, to find the mapping, you've got to find the y and so on, which is just solving that equation, inverting for the c sub x. Okay, I hope to come to some examples later on. In some of these examples you can find that mapping, other cases you can't. You just know it's given implicitly, but you can still check the conditions. Okay, so I would look now at interior regularity. So the question we want to answer is what are the conditions on costs and domains for local regularity. Okay. This is the problem. And I'm going to look at a classical approach. This is so in the 60s, there's a lot of work done on quasi-linear equations, quasi-linear divergence equations, solving smoothly Dirichlet problems. And part of the motivation for this work was then to connect to that Hilbert problem. I don't know if it's a 19 for 20th, but that asks about the smoothness of extremals of variational problems. So why study the smooth guys when you want to answer a question about the smoothness of extremals? And the reason is that if you study the smooth guys and you have some uniqueness in the small of the weak guys, then you have regularity. So that's the sort of approach we want to look at. So the classical approach would be to solve a classical Dirichlet problem in, say, a small ball. With boundary values given by the potential, which we can think of as a type of weak solution.
So last time there was a boundary condition. Is that just the mass balance that you
There is a boundary condition, but the boundary condition is somehow hidden in the formulation. T is a measure preserving mapping from omega to omega star. There's the mass balance condition. That's the boundary condition. But if I had a smooth solution, smooth diffeomorphism, then the boundary condition is precisely that T is going to map omega AE onto omega. If it's a diffeomorphism, then it's going to map omega onto omega star. I could have a smooth solution which is not a diffeomorphism. That means it's not going to reach all of omega star. Almost everywhere it would reach omega star. Okay, so we want to study, so that's the idea. Let's just take our weak solution. We know it's already Lipschitz. Use that as a boundary value, a small ball. And now, let's solve this Dirichlet problem if we can for a classical solution. So I'm not going to give all details. I just want to do enough just to detect the main features of the analysis that comes up. For example, when you start this process, you're going to be looking for a solution that's not going to be smooth at the boundary. Boundary data is only Lipschitz. And what you would do is actually you don't solve the original Dirichlet problem, you solve an approximating one and take a limit. So let me just leave that aspect aside, because those are technicalities, and we look at solving the Dirichlet problem for this equation. So let's write this equation in this form now. It's a Monge-Ampere equation. To T to U, I've got some matrix function. We'll put this x in, xu, and that's equal to some scalar function x du as well. And I know that b is going to be, b is positive, and these a's and b's are as smooth as I want. And suppose U0 is my potential now, U equals U0. So this is going to be in some small ball B sub r. So centered at x0. And U is going to be U0 on dBr x0. So I want to consider this type of Dirichlet problem for smooth solutions. Well, I would want to get, say, a U in C2. Let me just drop the x0. BR and say C0 BR bar. See one problem immediately. What is this A? No, sorry, what is the B? Well, you think, what is the B? The B's got a G sitting down here in the denominator. Now this Dirichlet problem has no relevance to that omega star domain where G is defined. And for the optimal transportation problem to make sense, G should be seen as being 0 outside omega star. So that means this function at the moment, this B is not well defined. It could be infinite outside omega star. And so B could be blowing up. And so I have to solve more than a Dirichlet problem. I have to solve this in such a way that I keep my mapping Y in omega star. That's the aspect that's going to bring in the geometric conditions on the boundary. So this is not a nice problem at the moment because my g should really be thought of as being extended to be 0 outside omega star. So keep that in mind as well, that g should be 0 outside omega star. So the problem is not even well posed at this stage unless I can deal at some point with this issue. But first of all, let's suppose that we've got g under control, that the image of y is omega star, and this, our g can be any positive. G is simply a positive function defined everywhere. Okay, so what's the key thing here? Well, the key thing really going to be the second derivative estimates. This U0 is Lipschitz. It's reasonable to expect I'll get a Lipschitz U out of this. It's semi-convex. The main issue is for a classical solution will be second derivative estimates. So we're going to need interior estimates for second derivatives. Okay, so if we want to do that for Monge-Ampere type equations, Hessian equations, we follow a procedure first used by Pogorelov. We're going to, first of all, I want to write this in a different form, taking logarithm. So we're going to solve for a new operator, log of determinant of the d2u minus dA equals the log of b. So with our conditions of positivity and smoothness, we just suppose that this log b is under control and at all its derivatives. So we take a new operator. I'll just use the same f again. And I'll write this a little differently. Let me just write this as a determinant of a matrix Wij, where Wij is my Uij minus my Aij. Okay, and then we differentiate twice in one direction. So let me differentiate twice now with respect to some fixed direction gamma. Okay, so this is very standard in fully nonlinear PDE, and there are some experts here who know that this is a concave function on symmetric positive matrices, and we differentiate twice. The term that comes up in third derivative is going to be quite a nice term. Okay, so do that, and here's one derivative. I'll use this upper indices for the inverse, so let me use this Wij to be the inverse of the W sub ij, and so we have a dij gamma u, k, and we differentiate one, so we're going to get the d of a pk of this aij, and this will multiply a uk gamma, and then there's going to be a minus an aij, and this is the derivative with respect to the x gamma of this term. Is that? So we get that, and this is just simply going to be a d gamma of the log b. That's one derivative. And do another one, and we'll get wij. Now we have a dij, and now I'll have this u gamma gamma. And now I'm going to take two p derivatives, and I'll get a quadratic form in the second derivatives. So I'll have a d pk pl of this aij, and then I'll have a u k gamma ul gamma. And just keep going. There'll be, for example, a d pk of an aij, and we'll have a u gamma gamma k, so a first derivative of this function u gamma gamma, etc., etc., etc. I put dots, I mean basically terms that won't give any trouble later on. And this will be a d gamma gamma now of the b. I know all about this. It's no more than quadratic in the second derivatives. So we know that the worst behavior here is quadratic and second derivatives, so just ignore it. And here's our good term. This is the Pogorelov term. It's a WIK WJL, and I'm going to have a WIJ gamma. By this I mean D gamma. Better write this properly because it's, remember, W is not a Hessian exactly at the moment. So it's D gamma WIJ D gamma WKL. Sometimes we call this third derivative the Pogorelov term. Okay, and let's just rewrite this a bit. I've got Hessians here, but my equations in terms of these W's, so we can switch to the W's and get more of these dots. If we do that. So let's write this in terms of W's. This will be a WIJ, and then we're going to have a DIJ W gamma gamma. I'm going to choose gamma as a coordinate direction with respect to eigenvectors in a minute, so you can think of that as one as a coordinate direction. DIJ that, and now I have this guy, my DPK on my AIJ. I'll have this form WK gamma WL gamma plus dot is good stuff. By good stuff I mean the growth is no more than linear and second derivatives, or third derivatives like this, which essentially behave like second derivatives at a critical point of this function, and over here my same stuff. And I know that this one is greater than or equal to 0 as well. That expresses the concavity of log determinant. Okay, now look at this. Everything that's in these dots is either a linear term in the derivatives of this U gamma gamma, or that could become a W gamma gamma when I do that, or it's sort of well behaved except for one term. It's this one. So the key terms here are this one. You can look at that one. Here we've got a WIJ here. That's not well controlled. Could be large. And here's something quadratic in the W. So this combination with this one and that one could be quite large. Could be growing like a power greater than 2 of the second derivatives. So it's definitely a very important term. And this term is a nice term. We know from the Pogorelov case, the case of regular Monge pair, if you want interior estimates, you've got to use this term. So we may or may not have to use this term. Okay, so the critical term is this guy. We'll write it this way. This is the critical term here. This is the term that will make or break second derivative estimates. And we'll write it this way: AKL sub ij, and we've got W K gamma WL gamma. What can we do with this? Okay, let's look at that. If this is, there's WIJ sitting here too. If this was sort of positive in a very strong way, this would be a very nice term. If it's just non-negative, it could be something that's thrown away, and we're back to the original Pogorelov situation. But look, just observe one thing, that the eigenvalues of the inverse here, of course, the reciprocals of the eigenvalues of these guys. So in one direction here, you're going to have a reciprocal of a maximum eigenvalue multiplying the maximum eigenvalue squared there. So you're expecting one direction, this term's going to go down to be a linear term in the w's, and then put with the dot dot dots. Okay, let's make that explicit. Let's take gamma to be one of the eigenvectors of my wij. So psi s and psi 1, psi n, these would be the eigenvectors at a point, the eigenvectors of wij. Okay, then we can write this term in the following way. Okay, this would be a sum over R, would have a WRR. Okay, so I'm just using these W's repeated indices for the eigenvalues now. So this is a reciprocal of the half eigenvalue of the wij. And I have my AKL ij. Okay, and now I've got a psi IR, psi RJ. And I'm going to have a WSS squared. I'll have a psi SK, and I'll have a psi SL. S is fixed and we're summing over R. Okay, so I'm writing things in terms of decompositions into sums of dyadics, basically using the eigenvectors. Okay, and we can write this then as a sum where R is not equal to S. All this stuff. Yeah, this same stuff. R not equal to S, all that stuff. And then I can put R equal to S. And I put R equal to S, I would simply get a KL ij, this sum psi I S, psi j S, psi k S, psi L S, and then we'd have a W S S. So it's a lower order term. We can include it with the other stuff. And so I'm left with this term here, the sum of where R is not equal to S. How do I control this? Well, we've got a sort of form here. It's an AKLIJ, psi I, psi j with an R there, and a psi k, psi L with a NS there. And I know that if R is not equal to S, then these eigenvectors are orthogonal. So I can say straight away that this is going to be greater than or equal to some constant C0 times the trace of this WI, so sigma WII, times WSS squared minus dots. There's one, when I do this, there's one term to throw out as well. This is the sum overall. I can say it's greater than or equal to that if I have such a condition that the A, I, J, K, L, psi I, psi j, eta k, eta L is greater than or equal to C0 for all psi eta mod psi equals mod eta equals 1 psi orthogonal to eta. And we'll take a C0 could be greater than 0 or greater than or equal to 0. So if I have a condition like this, kind of upgraded ellipticity condition, then in fact you should think of this as a supplementary ellipticity condition. If I have such a condition, then I have this very good control. Okay, so now there's a couple of situations here. If this C0 is positive, this is an extremely strong term. It wipes out any of these, wipes out quadratic terms on the right-hand side. It wipes out anything that's going to have third derivatives in some sense. It's a very strong term, and it's so strong that you can run, you can multiply by a cutoff function. I could take the sum over S here. I could just take the S, which gives me the maximum eigenvalue. You could run through with a cutoff function and still get an estimate. I could even take the gamma to be a variable vector field, say, which is tangential on the boundary, and still get estimates, because this term is so strong if the C0 is positive. It's a very strong term, kills everything else. If the C0 is 0, and of course this becomes a neutral term, and any estimate is going to have to depend on this Pogorelov term. So we have these two situations. Positive C0 basically means I can proceed to estimates, and very strong estimates, genuine interior estimates. If the C0 is 0, then this term is neutral, doesn't do anything for us, and everything, all the work has to be done by this term, which is the case in the Monge-Ampere equation, Cxy equals x dot y. So we have these two situations. So I'm going to really talk about the good situation today. From a PDE point of view, this situation is unnatural. It looks like a fudge. But we would have said that 20 years ago. But now, because of these applications and the applications to conformal geometry, it's a bit not so polite to call it a fudge anymore. It's a term it's a situation that comes up naturally. And what's also important is that if we don't have this situation, C0 equals 0, but in any example, you can actually approximate by those situations where the C0 is positive, which if you wanted practical applications in optimal transportation, then that would be a reasonable thing, never to have C0 equals 0 if you can approximate it by a C0 positive. So this is not so bad, this condition. So let me now add this to our conditions, and we'll call this A3. Got this A, KL, psi I, psi j, same, just write it again, psi I, psi j, eta k, eta L, greater than or equal to some C0, and I'll just write psi squared, eta squared there for all psi dot eta equals 0. We should also say that if we don't have the condition, then we know here there's going to be terms that grow faster than a quadratic power. And there's absolutely no way they could be estimated by the rest of the terms in this differentiated equation. So that means that if you don't have this, if you don't have the C0 greater than or equal to 0, you would not expect any regularity at the second derivative level. If you have it equal to 0, then okay, you'll have to work hard because you have to use the Pogorelov term, but if you have it positive, then life is easy, easier. Okay, so we assume this A3, and this implies, and then once you do this, then it's pretty quick. You have a genuine interior estimate. I'll call this genuine interior estimate. It's an estimate that's only depends on local behavior near a point. So a genuine interior estimate, that the sup over any strictly contained subdomain of D2U is less than or equal to C. And this C would depend on omega prime, omega, and all the stuff that comes up in these differentiations, or the C2 norms of the A's and the B's, and the gradient as well. Sup of the gradient of U and A and B.
So
Yes, I've just, what I see is optimal transportation. You've got this mapping going into this omega star, and the gradient is given by this relation, the Cx derivative. So if omega star is bounded, automatically the gradient is bounded. So the gradient bound comes for free. So in optimal transportation, so any estimate, an estimate depending on the gradient here is not a big problem. This will be a problem when we come to our application, though, because it's not just a matter of having a bound on the gradient. We've got to control that. We've got to control this situation as well, and that's not going to come from. That's going to come from very much from the optimal transportation side. That control. Okay, let's just jump back to OT, to the optimal transportation now. So OT, in optimal transportation, we know that Aij is two derivatives of respect to x of a cost function, x and then at this y. So we can see, make a couple of observations straight away. If I write out in terms of the C, this ijkl, so it's going to be a Cij, write this out. Now I need some notation with these C's. Anytime let me use this Cii dot 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 k dot 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 to mean d by dxi dot 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 of C d by dxi followed by d by dyk, etc. of the C's. So if I don't put the dots there, if I have a string of indices there, then I separate them by a comma. Before the comma I mean x derivatives, after the comma I mean y derivatives. So we use that notation. And let me also use this notation that the Cij is the inverse of this Cxy. So that's just some notation we use in optimal transportation. And if we calculate in terms of the C's, this is going to be a Cij, a PQ, minus a CRS, Cij, Cij R, C, S, K, L, and a C, P, K, C, Q, L. In our paper with Sujia Wang and myself and Shina Ma, it's actually it's done using this condition. This calculation with second derivatives is done directly on this condition. It was only afterwards we realized the connection back to the P's, not the first draft of the paper, but in a later draft, condition back. But if we write it this way, then you'll see something straight away, because these are singular matrices, and remember this form hits an eta, so immediately you said this condition is symmetric, because I can just transform those vectors eta by these guys and write the condition in a symmetric way. So this is symmetric in x and y. So that's one property. And a second property, think of what this quantity is. I'm differentiating twice with respect to a gradient. Fix the y. Let's fix y. Just fix y. I'm differentiating twice with respect to a gradient of a scalar, the Hessian of the same scalar. What does that tell me? It tells me immediately it's a 2-2 tensor. So already you have a condition which is like ellipticity. It's invariant under coordinate changes. So another reason for calling it a sort of supplementary ellipticity. Okay, so it's a natural condition. We had the referee comment on this first paper saying the condition was very restrictive. If you didn't quite understand, because from my remarks about the twice differentiated equation, it's already a natural condition. And hopefully at the end of this, of the second hour, I'll mention the result. And in fact, this is actually the sharp condition for the A3W is the sharp condition for regularity. It can be proved not by waving your hands at a twice differentiated equation, but it can be proved directly by construction of an example. Okay, so now we have the conditions that we would want on the cost functions, this A1, A2, and A3. And I should also mention that really we should be seeing what we can do with the second paper, Suja Wang and I called the degenerate version A3W. That's with the C0 equal to 0. Because that's the one where you cut off, it's the cutoff one for regularity. But again, the difference is you can't do anything here about the Pogorelov term. And we know already from the Monjan pair that you do not have genuine interior regularity with, in that case, you can't have an interior estimate like this. The estimate does depend on some global behavior. So this estimate is already sharp in a sense. Okay, now I want to go to my Dirichlet problem. And how do we overcome? So I have the crucial estimate. Supposing I can control the gradient, then I have the crucial estimate in that Dirichlet problem. How to control the gradient. Okay, so let's find out what the domain condition should be. I'll just simply try to solve that Dirichlet problem, and at some point we'll have to do something with our domain. Or one of our domains. There's two domains here, omega, omega star. So let's look for the conditions on domains. This whole thing is quite interesting because the estimate does not tell the whole story. And it's a situation in PDE where the framework itself is extremely important. The estimate, usually have estimate, boom, job is finished. Here, it's building the right framework is extremely important. And what we have to do is we have to set up a generalized Alexandrov theory. So we need the theory of generalized solutions. We need a theory of generalized solutions. In the sense of Alexandrov. No. It's going to be. I've got this problem. I can't even approach this Dirichlet problem unless I can do something about this. Because sitting on the right in the B is the G in the denominator. So at the moment the B is infinity if my Y goes outside omega star. But the Dirichlet problem has nothing to do with this Y star. So somehow I've got to be able to, I need some condition, and you see it's not going to be a condition on omega, it's going to be a condition on omega star. So I need some condition that tells me that when I solve in this, if I have a solution of this equation, that already is going to tell me that I stay in my target, my vector field Y image stays in omega star. I need to somehow deduce this from the equation itself, from the Dirichlet problem itself, before I can do anything. So that's where a domain condition is going to come in, and it's going to be a condition on the target domain. And you know from the old work in quadratic costs. The condition is convexity of a target. So it's going to be some type of convexity, but the question is, okay, what type of convexity? Let's find the convexity condition. Okay, so now I start off with a function which is C convex in omega. So the Alexandrov theory is a theory of generalized solutions of Monge-Ampere equations. At the moment, sure, we have a generalized solution, but it's in the sense of solving this optimal transportation problem, which is about pushing a measure forward to another measure. We have to relate that to another notion, this Alexandrov notion. So let's go back. We follow Alexandrov and Backelman and people. And we define a notion of C-normal mapping. And so chi of u at x0. Now let me do it this way. I write a chi sub c of u. So that's going to this quantity chi sub c of u is going to be a mapping. This is called the C-normal mapping. It's a multi-valued mapping. This is going to be the set of y in. No, okay. Keep these RNs here. Generally, will be some restriction on the y's, such that u of x is greater than or equal to u sub x0 plus cx y minus c x0 y. So here's my C convex function u. I know at any point I have this support C affine function from below. That will function itself will be defined by some point y, and the set of all such y's is then the normal mapping at x0. So this is the same as the old definition for convex functions. Of course, what's important here is that I have this support must be a support across all of omega. So all these quantities are also functions of omega. So whenever I have quantities like that, I'm not writing the omega here, but clearly these depend on omega. So, for example, if you have a cone, this is, and you have the x dot y, this is all the slopes of these support hyperplanes at the bad point. At the good point, it's just going to be you just get the gradient back. So it's kind of a multi-valued. See, in the optimal transportation problem, we had Lipschitz functions, in fact, semi-convex functions, and we didn't care about the singular points. Now we have to care about the singular points to go to do anything else, because if we're going to take limits, those AE definitions are not preserved by limits. So we have to worry about. We therefore have to take account of the singular points. So what we have is we have a whole theory of weak solutions, generalized solutions, which extends the Alexandrov theory for Monge-Ampere. So let me just come back here. Stay on this side. So before I had a mapping T, and the mapping T was only defined almost everywhere. But basically what I'm doing now is I'm defining it everywhere. So it's defined as a multi-valued mapping at the singular points. And if u is differentiable at x0, this would imply, of course, that chi u x0 is simply chi CU is just my t, my mapping t at x0 tu. It's the y of x0 du of x0. Okay, and there's another relation here which is important. That chi cu at x0 will always be contained in the image under y of the subgradient of u at x0, where I'll define the subgradient this way: du x0, it's really d minus, coming from below, u at x0 is then the set of p in Rn such that u sub x is greater than or equal to u sub x0 plus p dot x minus x0 plus little o x minus x0. So we would always have that this image of the C normal mapping belongs to y of the subgradient. Always have this. And we can ask a question, and of course at the points of differentiability they agree. Everything is single valued. We can ask this question when I'll collect these questions, because I asked one last time: when does locally C convex imply globally C convex? This is the same sort of question, right? Because the subgradient is a local quantity. The C normal mapping is a global quantity. So we could ask the same question: when do we have equality here? When can be replaced by equals? So the second question we've collected. I'll answer all these questions at the end today. They all have the same answer pretty well. You're going to see this question in a moment as well. I'm not going to avoid it.
What's your question again?
So if you look at, see, this is the set of y's for which we have this global support function lying underneath. Now the subgradient is kind of derivatives where you have a sort of contact from below, but modulo little o. So this one is clearly smaller. Any y in here is definitely going to give me an element of the subgradient, because I'll certainly have the other contact. So, and we know for convex functions, if a convex function, then and you have a hyperplane underneath it, if it's globally convex, then the hyperplane will stay underneath it. So for convex functions, this is the same. These are the same. All these questions will be a question like when can you replicate the behavior for regular convexity? When is locally convex imply globally convex? When is the are the local supports the global supports? You could say it that way as well. Okay, so now we can define a generalized Monge-Ampere measure. I'll just work up to this definition of generalized solution and we'll take our break. Okay? We can define a generalized Monge-Ampere measure. So define it this way: a mu C U Borel set E is equal to the Lebesgue measure of the image under chi of E. That's fine, but I have to prove this is a measure. We'll just skip that. But this is a measure. And we could also talk about an extension of what Backelmann calls an R curvature. We could define a mu CG u e to be the integral over this g over chi c u e. So this is an extension of the Alexandrov introduced quantity for convex functions. And Backelmann introduced quantities like this for, called them R curvatures. We have a function g, a density g. And these are all the cases where cxy is x dot y, these quantities. And g would be a given non-negative function, L1. Now we can make a definition that function u, which is C convex in omega, is a generalized solution of the OTE in omega is equivalent to simply that mu C g of u of E is the integral of f over E for all Borel E. So that's an extension of the old notion of Alexandrov, old definition of generalized solutions. Oh, and then keep in mind that I better remember, what about this g now? So g is not in the denominator anymore. I really want g to be, keep in mind, g is extended to be 0 outside omega star. Remember, g equals 0 outside omega star. For this, I could take any g, right? But remember, just remember in our case, in the OT situation, right? This makes sense for any g, L1 of Rn, L1 log of Rn. This makes any sense for any g, but keep in mind when we're going to make a connection, we want the g to be 0 outside omega star. Okay, shall we break now and then? Okay, we're ready to roll again. Right, just state this proposition. It's proven in the paper with Wang and Ma. If we have A1, well, I'll keep putting A2. Maybe it's not necessary here. A1, both sides of A1 are important. Plus the mass balance. Then, if U is potential, that's the first component of a solution of the Monchkin-Torovich problem. Then that's equivalent to U being a generalized solution. So that, and this would mean that integral of f over E is the integral of g over chi cu E intersect omega star for all Borel E in omega.
Mass balance?
Oh, the integral of f being the integral of g. Yeah. The mass balance is the integral of f over omega is the same as the integral of g over omega star.
Okay.
That's absolutely critical in showing that. Yes, yes, yes. This is of course a pull-back solution rather than a push-forward solution, and you can guess then it's that almost everywhere one-to-oneness which shows that. So you just couldn't take a potential which, even though it's uniquely determined AE, and conclude this. You need the one-to-oneness, and to go back the other direction, you need to show that the C transform of the generalized solution is itself a generalized solution of a dual problem, and you need, so in both directions you need a kind of dual result. And that's the main ingredient in showing this, plus seeing what this means in terms of images as well. Okay, so why pass to these generalized solutions? Now we'll start to give some of the reasons why. This is just continuing with the Alexandrov theory. We have a monotonicity result. We have a situation like this. Here's a C convex function V lying above a C convex function U, and U, so less than V in omega, and U equals V on d omega, maybe less than or equal to. Then the image of the C normal mapping of U on omega contains the image of the C normal mapping of V on omega, and so the measures have a satisfying inequality. The Monge-Ampere measure of U of omega is greater than or equal to the Monge-Ampere measure associated with V of omega. And now the proof is standard in the Alexandrov theory. We simply take a C support for the V, and we move it down, move it right down below the graph of U, then bring it up again, and it will contact the graph of U before it contacts the graph of V again. So a C support for V will be a C support for U with the same Y0. So immediately we have this relation, and then of course the definition of the generalized Monge-Ampere gives us that one. So in passing to the generalized solution, we actually end up with a kind of this monotonicity property. But from this monotonicity property, we could conclude some sort of comparison principle that if this measure satisfied a condition like that, then you could not have the reverse. So if the measure satisfied if you had a condition like that, you could not have the reverse inequality, that the V was greater or equal to the U. So that's going to be a basis for a comparison principle. This is going to give a comparison principle for the Dirichlet problem. So that's one application.
So you are saying, so these are assumption and those are the conclusion?
No, that's not a conclusion at this stage. This is going to be an application.
So
I haven't put a formulation here. Yeah, if you have this configuration, the U less or equal to the V, no, just any old C convex functions. Arbitrary no solutions, just arbitrary C convex functions. Arbitrary C convex functions, and you have this inequality between them, then you'll have this monotonicity property of the measures. So this is well known, for example, in this Alexandrov theory for convex functions. You simply take the hyperplane and you move it down. Now, of course, so and the C, of course, is quite arbitrary for this. I wouldn't need any conditions on my C to do this. So, but that's an immediate byproduct. We actually now have something that's looking a little bit like a maximum principle in elliptic equations. There's another application too. We won't need that, but what if I got a sequence of functions converging uniformly? Then it turns out that these measures converge weakly. This is one of some things stated incorrectly in the paper with Wang and Ma. There it says local uniform convergence. It actually has to be the full uniform convergence. So this is a sort of another result, and we won't need, is that these measures are weakly continuous with respect to full uniform convergence. I want to just have the local uniform convergence that belongs to the same sorts of questions that I've been asking already. Those questions are all about localization versus globalization. Okay. Now let's use this in our Dirichlet problem. So now we'll go back to the Dirichlet problem. So here's our small ball. We have some given function u0, which we now know is a generalized solution. There's a u0 there. And I want to solve for an elliptic solution with the same boundary values, some u. Okay. And this is this small ball, B sub r is in my big domain omega. Now what I claim is that this u is going to be greater than or equal to the u0. Okay. Now, my u is an elliptic solution. It's not necessarily C convex, but it's quite easy to see that if my u is a smooth elliptic solution, I make my ball small enough, it's going to have to be C convex. That these local supports can't jump up that quickly because things are smooth if they have a strict contact, and the ellipticity tells me they would have a strict contact. So they'll actually be C convex. And not only that, but I can kick them, so I get strict super solutions. And I can look at a small set where u is greater than or equal to u0, and I can apply my comparison principle and eliminate that possibility. I can apply the comparison principle because I'm not working on my omega anymore. I'm working on a small ball. So my signal map is changing. But on the small ball, it gets larger. It gets larger. So I can do a one-sided comparison. So we can conclude u greater than or equal to u0 in BR. Right? So we can do a one-sided comparison. Since mu of the u0 increases on this when non-decreases, I mean, when it increases when omega is replaced by, no, sorry, other way around. It increases, that's right. There'll be more contacts on the small guy than the more support hyperplanes on the small guy and the big guy when omega is replaced by BR. So I can do a comparison like this. Okay, so that's.
Not getting lost. What's the condition satisfied by u?
I'm being.
U and the u naught
Oh, they would agree on they would agree on the boundary of this small ball, right?
On boundary of this BR.
But now I look at some component where the u goes above the u0. And now I work my comparison argument, because the comparison argument doesn't have any conditions on the boundary. I work that comparison argument, I then contradict this on such a set. First of all, forcing the u to be modified so I get a strict inequality. And taking account of the fact that when I go from omega to the small ball, I do not decrease this Monge-Ampere measure. Remember, the Monge-Ampere measure at the moment is domain dependent. So we have this u greater than or equal to u0. So that's coming from the monotonicity. But then, what else do we get? I can use this one. This one tells me that the chi c of the u is going to be contained in the chi c over this BR is going to be contained in the chi c of the u0. Aha. Fine. Of BR by my monotonicity again. Fine. Now, all I have to do is show that this doesn't go outside omega star, then my Dirichlet problem is well posed. That I control that G away from 0. So we need, therefore, hence, we need chi c u0 BR contained in omega star. We can take closures all the time. We need this. At the end of the day, I'll just make my G uniformly positive in omega star. We need that so that we need to make this B term behave. So, so what's the condition that keeps this image inside omega star bar?
What is U0 to start
U0
with?
is my potential. I assume that U0 was a potential solution of the Monge-Kantorovich problem, the potentials, and then I now know it's a generalized solution. These monotonicity results are true. If I have an elliptic solution, then in the small it's going to be a C-convex function. I know that much, and I know I can, if I have any smooth elliptic solution, I can force non-strict inequalities to be strict inequalities. So these ingredients have gone in here to get this control.
This is only suppose this is a sufficient condition.
Yeah.
You want the chi c of this.
If the chi c u0 went outside, I would never ever be able to control that. So yeah. But there is also, at the end of the day, there is a counterexample to show that the condition I'm going to give is necessary. So that shows us that we can control the gradient already just from the problem itself, just from the boundary value. So this is unusual. You know, in barrier arguments for elliptic equations, Lipschitz boundary value doesn't control Lipschitz solution. You need something like C1 alpha. But here, with these monotonicity properties, we're controlling the gradient of the solution in some sense by the gradient of the boundary value. Okay, so now here's a proposition, and this is the key thing. Let's start with a definition. Now, what's all this coming from? I'll just go ahead. what do we know about this chi c? What do we know about this at a singular point? Now I used,
You really allow
I need some theory from, I need some subgradient theory. I didn't quite define the subgradient in the proper way, because when you define a subgradient, you should be taking limits from neighboring points. But my functions are semi-convex. And there's a result in optimization theory, maybe Clark or I think, that says that if you have a semi-convex function or something, certainly has to be more than Lipschitz, then these two notions are equivalent. So it means that, first of all, the regular subgradients are going to be convex sets. If my function is not convex but semi-convex, the subgradient mapping will still be a convex set. And not only that, but its extreme points can be approximated by good points. So that's coming from the theory of Clark and Rockefeller and all these people. I can still approximate extreme points by good points, and these sets are always convex sets. And when I pass from the subgradient to my mapping, then I know that the image of these guys lies inside the mappings of the subgradients. I don't care about whether they're equal, it lies inside. So that's telling me that somehow images of the same images of these sets omega must be convex. Corresponding images of omega star must be convex. So we make our definitions now. These are the important definitions. We say that omega is C convex with respect to, let's say, some set E star. Just call it E star because it could be 1 point, some E star in Rn, if all these images, Cy of omega y, are convex. All these sets are convex for all y in E star. First definition. And second definition, omega star is C star convex. So it's the dual definition with respect to some set E in Rn if these CX's of omega star, X omega star, if these ones are convex for all X in E. So these are our definitions. The proposition is that omega star, C star convex with respect to omega implies that this result chi u chi sub c of u of omega is contained in omega star bar.
You don't worry, touch the boundary.
No, I don't care about the boundary, because if I'm working with smooth functions and a uniformly positive R and something that's positive, the boundary is not going to bother me. If I approximate my G, for example, by something which is positive on the boundary or even positive slightly outside, it's not going to bother me here. I could extend my G outside by epsilon and approximate back later. But we can't avoid the omega star bar. That can't be avoided. So that's the key proposition in our work, and that's how the C convexity was discovered. So, from a not the most obvious way to think about it, but that's how it was found. I've already sort of sketched the proof. By the way, always, in all these things, we must assume that mass balance condition when we're working on these things. So here's the sort of proof that if, so we have in omega, we have good points and bad points. We have the points of differentiability and we have the singular points. If a good point goes outside omega star bar, that's where the bar's coming in. Then there's going to be a neighborhood outside. AE neighborhood outside. You're forced to have a neighborhood outside. That's because if you've got a good point, you can write it as a limit of other points. If you have a good point here, x0, then if you take any sequence x approaching to x0, there's going to be a subsequence of these support of these y's approaching the image. So if one point goes out, then a set of positive measure will go out which contradicts mass balance. So all the good points go in here. Now, if you take a singular point and just say look at what I've said, if you have a singular point, then we have this multi-valued image for the C-normal mapping, but the extreme points can be approximated by good points, and it's the convex hull of its extreme points. So the convexity condition, that convexity condition will keep me in here. So the proof then follows from the properties by the properties of the chi Cu and the convexity of chi Cu x0 and the approximation of the extreme points of that set by points of differentiability, points where U is differentiable. That's one of the important ingredients in this whole story. Okay, I'm not done. Actually, we were done at this stage in our first paper. We forgot, we didn't forget, but remember I used the comparison on one side. So this tells me that the Dirichlet problem is well posed. Okay, there's a lot of machinery in fluid nonlinear equations. We approximate by smooth boundary values, need barriers to estimate derivatives at the boundary, take a limit, and we solve the original Dirichlet problem. Fine, we get our solution U. We know already it's greater or equal to the U0, okay? But we don't know that it's less than or equal to the U0. However, when we wrote that first paper, we did the standard thing in classical elliptic equations. You want to prove uniqueness. You carefully prove one side, U greater or equal to V or whatever, then you wave your hand for the other. So hidden in this paper of ours is such a hand waving, ignoring the fact that we're working with a different measure on the smaller domain, possibly. So so I can say we've almost proved a result. So almost proved that if you have A1, A2, A3, and F, G, smooth, positive, and uniformly, so everything nice, that this implies potential U is locally smooth. So almost proves. And what is missing? We're still missing that the U less than or equal to U0, the other half of uniqueness. The other half of comparison principle. Well, this would be fine. This, of course, would be fine. This would be fine if, again, if I know that my chi c u is exactly y dot du. That would tell me that the definition of Monge-Ampere with respect to a subdomain is the same as the definition with respect to the full domain.
In general, this is a subset, and the purpose is to show this y avoid this omega star closure. But you only have this subset.
Yes.
Then why should it be enough?
Uh,
I'm getting a little bit of
sorry, you have the subset, but that tells you that the PDE is well defined. You solve that PDE for the smooth guy. You then use a local uniqueness to show it's the same as the original guy, because it's got the same boundary value. Well, up to now, I haven't got that local uniqueness in place. I've only got one side of it. And the other side would be automatic if I knew this.
and then you use that.
And then I'd be done. So we almost proved the regularity. Okay, so if we can answer this question under the same assumptions, then we're done. And well, let me just, this is kind of stuff from another paper. In fact, this is, I just mentioned that we could answer this question if we went straight to C1 regularity. This would also be okay if this set was always single valued. So if we had C1 regularity, and also fine if potential is already C1. Okay, because then these are both single valued. So let me just make a digression about C1 regularity. I could define the notion of a contact set. Let's have a C-convex function. So U is C-convex. And let's take a point y0 in the C-normal mapping of U at an x0. And we can define a contact set. And I'm going to be a little bit rough now because it's only a quarter of an hour to go. Define a contact set gamma, which is now going to depend on x0 and y0. This is the set where we have equality that inequality becomes equality in the condition for support functions. So the u of x is the same as the u of x0 plus the cx y0. It's a set of x in omega such that u of x is the same as u of x0 plus cx u0 minus cx0 y0. So okay, the contact set is a set of points where we have contact. Okay. I could ask the next question. When is this contact set? When is gamma a C-convex set with respect to, say, the C-convex with respect to the, say, chi C U? Yeah, with respect to, say, that set. When is that gamma? C-convex, or C-convex with respect to, say, the point y0? No. And if gamma is, so it's another question, And if gamma is C convex with respect to such y0, we get a very fast proof of C1 regularity. We get a similar proof of C1 regularity for this f over g bounded, some constant. Okay, now I'm going to start really the hand waving. Why is that the case? Well, you do this by how to do this. To do this, we prove that the C transform, right? This is the dual potential, or the dual potential is strictly C star convex. And now just make a very fast, how do you prove this? Almost the same way as the regularity. You have this set where there might be other contacts, but the set's C convex. You pull a very small ball out, take a very small ball around a point in that set in such a way that the complement is no longer C convex. Now, in this small ball, we solve another Dirichlet problem, but now we have everything under control. We solve in this small ball, we solve the f of u equals some small constant, some delta, less than the g over the f. When we go to the dual, we turn these things around, less than g over f times, well, other things, maybe the cxy or cxy is there, determinant. We solve it, so we solve a small constant Dirichlet problem. Take the ball small enough, what we get is going to be C convex, and then we simply take this, that guy is going to lie above, same argument as before, going to lie above my original guy. I take the sup of the two, it's C convex. But now the contact set is going to be this complement here, not C convex. I have a contradiction unless I have a strict C convexity. So very fast argument to pass from an answer to the question about when is this, if this is C if you know this is C convex, there's a very fast answer to pass to, very fast way of passing to C1 regularity by solving a Dirichlet problem. So there's another way I could deal with this question instead of this question, but these are actually dual to each other in some sense. So it's really versions of the same question. This has one advantage in doing this first, is that, and this is related to what Alice was asking, she worried about the closure. Well, in that regularity result, and it's not spelled out in our paper, I really have to have my G nice up to the boundary. If I come through this way, all I really need is that this G over F is bounded from below, the F over G is bounded. So there are some advantages in coming through this path. But now we have another question. When is...
So what is the C transform that gives you this dual potential?
The C transforms I defined last time. It's this sort of like the Legendre transform,
Oh, okay.
but it's with a dual potential. You just turn the equation round, F is replaced by G, C sub XX becomes C sub YY in the equation, D2V. You solve that one. Basically, the result is that if you have a property, the result would be that if you have a property like that, then you have you have you have strict convexity under conditions A1, A2, A3. Strict C convexity. Okay, I'd hope to keep going with proofs, but this is going to have to be cut short. Raised all these questions. When does local convexity imply global C convexity? When is the we have equality in this relation between the C normal mapping and the subgradient? When is this contact set C convex? I could ask that this is a limit of a question about sections as well, sub-level sets. Ask all these questions. It turns out the answer are the same conditions. So this is the sort of one of the main properties of C convexity. That if you have A1, A2, now it's enough to have A3W, and all these things are true. That local C convexity, okay, of the C2 functions implies the global C convexity if the target, if T of omega if omega is C convex with respect to its target, TU omega. That's 1. 2, we have that this chi CU omega will be this y dot du, and we have 3 that if omega is again C convex with respect to chi u chi C u, then this contact set gamma is C. Gamma is C convex. So all these properties, which is telling us that the C convex functions behave like regular convex functions, they all depend on this A3W. So this, a lot of this was picked up in a subsequent paper by Suja Wang and myself, but using a kind of, for these particular results, a kind of clumsy method. It's like proving that local convexity implies global convexity by contradicting saddle points if you have a local contact and going to the boundary and using the curvature as a positive. You can do that. Picks up all this type of stuff. In some sense, that was fine for us because we needed to confront boundary curvatures anyway in other situations. Much better approach about the same time by Kim and McCann. I call that the direct approach. You don't shove things to a boundary, you just work directly inside the same way you would, analogous to the way you would prove local convexity implies global convexity by using Taylor's formula along a line segment. And the upshot is that these two approaches will give you all the same stuff in the end. And it's all these things. And there's a nice lemma which gives you everything, actually, it's an extension of this result for convex functions, that u of x minus u of x0 is greater than or equal to du at x0, x dot x minus x0. Convex function in a convex domain, you have this property. And there's an extension of this property to the C-convex functions. There's an extension of this, also proved by Taylor's formula, but not the same, much more complicated use of Taylor's formula than in the convex case, different use. But there's an extension of that, and all these come out almost as immediate corollaries of that extension. The whole three, it comes out like one package. So I had hoped to go through these, to do part of this proof. So this really should be the start of the story. You define this notion of C convexity and prove these basic properties, then get on with the regularity story. But this stuff sort of came after the regularity, and partly was used to correct or to complete the regularity theory as well. Let me also mention that A3W is necessary for these two. It's not necessary for this one. The target one-to-one mapping with one-to-one smooth mapping with C star convex target would be enough for this one. It was in another paper of Suja and Wang and myself on global regularity, but it's necessary for these. And also this A3W, this has shown a couple of other things, conditions. That C star convexity of the target is necessary for C1 regularity. That was proved in the original paper with Ma, Wang and myself. And then you don't have to do much more than that, but it was noticed by Lopere that proof, that you can actually connect that proof up to the violation of A3W. You violate A3W in the same situation. You're almost in the same situation where the target is not C convex. You have a C segment, C star segment falling out, going outside the domain, and that. So that A3W is necessary for C1, arbitrary densities. The C star convex image is also necessary. Ideas are much the same in both proofs. So that this theory is essentially complete, and there's also other C1 results, C1 alpha results I haven't mentioned. Theory is basically complete, except we don't fully understand the intermediate degenerate case, the A3W. Okay, so half past, I could have. Yeah, sorry that I had to truncate the story at the end. Okay. Well, I haven't given all the examples either. It takes a while. There are a lot of interesting examples here as well of functions that satisfy these conditions. It's not that restrictive a condition, and there are some very nice examples. And one of the nicest is the geodesic distance squared on the sphere, which was shown by Lopere. Okay.
So this, when this A3 condition is not satisfied, this example shows no
When the weaker one, the A3W. So the A3 is the strong one, and you have all this really good stuff. And you have, for example, very good C1 alpha estimates with alphas much better than you would have in regular elliptic situations. And then you have this degenerate one, the A3W, and that's not fully, we know a fair bit about that, but not fully understood. And then, but you know, if you violate the degenerate one, then you don't have regularity for arbitrary densities. So this type of condition and this tensor here is extremely natural. And I imagine you'll hear more talks during this year on that tensor on manifolds. That's not really understood at all, because even on the manifold you'll get different. You can vary the manifold and you get a whole lot of cost simply by taking the geodesic distance squared, and then that condition is a fourth order condition on the metric. And that's not understood.
So in that case, this condition is satisfied.
And the sphere, it's satisfied. Geodesic distance on the sphere squared satisfies that condition. But so far, nobody's proved it on ellipsoids, apart from those very close to a sphere.